May 27th. 9 scientists from the CENBG, Center for Nuclear Studies in Gradignan near Bordeaux, are on their way to California to put the GLAST satellite into action. Well, it's called GLAST now, but as you know, NASA is superstitious and only truly christens its satellites once they are in space and working. Word has it that it will perhaps be called Enrico Fermi, after the famous physicist, but for now it is GLAST, which stands for Gamma Ray Large Area Space Telescope. GLAST is a telescope orbiting the Earth that will look at the sky in a different kind of light, gamma rays. It is not the first of its kind. EGRET was launched in 1991. Where EGRET took great still photos, GLAST makes movies. Look at the sky above the Earth. 100 billion stars surround us in the Milky Way galaxy where we live. We know a lot about stars like our Sun, but we still know little about the massive stars 10 to 100 times bigger. Yet, these stars generate most of the carbon, oxygen and iron in our bodies. One of the aims of GLAST is to film these massive stars, or rather what's left, hundreds and thousands of years after their deaths. At the end of their lives, they explode with unbelievable violence and create a huge cloud of stardust. A star smaller than Paris is born in the heart of the cloud, heavier than the Sun and turning 10 or even 100 times per second. The star emits a beam of radiation, and from Earth you see pulses like the flashes from a lighthouse or from the revolving light on a police car. It is called pulsar for pulsating radio source. Some of them also emit gamma rays, which are of special interest to astronomers as they are hyper-energetic and provide new information, in color so to speak. Rather like a doctor who looks at his patient with X-rays or with a CAT scan to make a good diagnosis, GLAST will film gamma light. The universe goes beyond the Milky Way. Gamma rays reach us from eruptions in the cores of distant active galaxies called blazars. But what are gamma rays? They are invisible light. Remember the electromagnetic spectrum? The part you can see goes from blue to red. The part that you cannot see is well known and includes the infrareds and ultraviolets that can hurt our skin. There are also radio waves and X-rays which we use daily. Most gamma rays coming to Earth don't reach the ground as they are blocked by the atmosphere. One way to see them is to go and find them in space. It is not by chance that researchers from the CNBG are leaving to put GLAST into action. David, high-energy particle physicist. Denis, researcher in astroparticles. Lucas, a doctoral student. They are the specialists in precision timing and clocks. Benoît and Thierry, nuclear physicists. Damien, doctoral student. Vincent, postdoc. They specialize in the gamma color, that is the energy. Marianne, young and brilliant from the prestigious École Centrale. Marie-Hélène, a doctoral student. They specialize in the cloud matter surrounding the pulsars. What is their role in this project? Firstly, to perfect the apparatus designed to see the color or energy of the gamma photons. It is called a calorimeter. The basis of this instrument is a salt, king-size, extra-large salt. Its scientific name is cesium iodide. Let's explain this. When the gamma photons hit the telescope, they transform into a particle of matter, an electron, and another of antimatter, a positron. No need to go into the physics principles. Just remember that it comes from Albert Einstein's well-known E equals mc squared. Anyway, when the electrons and positrons go through the crystals, they react with the salt atoms and put out some blue light. They scintillate. The more gamma energy, the more light they make. Actually, it is a little bit more complicated than that. The calorimeter has 1,536 salt crystals, each weighing a kilo, a structure made of carbon fiber composites, and a zillion electronic connections. The calorimeter is the fruit of a collaboration with the French National Institute for Nuclear and Particle Physics. The calorimeter had to be tested in giant particle accelerators that speed up ions and gammas like the ones in space. Several times the small team filled a truck with equipment to drive to Geneva, to Caen or even to Darmstadt in Germany. On site, it wasn't always plain sailing, as a particle accelerator is not easy to come by, and time is precious. So, during the testing periods, nobody sleeps much, there's no time for sit-down meals, and everybody lives on coffee. Delays to the schedule are frustrating, and everybody keeps fingers crossed that all goes to plan. On top of this, the Bordeaux team added a precise system to check the satellite's clocks, because GLAST is meant to make films. The movies must be properly synchronized time-wise. But to return to 27th of May 2008, GLAST will have been in orbit for 10 days, 600 kilometers above the Earth. The telescope is going to be powered up. In the control room in California, the CNBG crew will meet up with the teams from all over the world that built the telescope. The picture will be adjusted, the last details seen to, and the precision clocks checked, so that in a few weeks GLAST will be able to provide its first gamma-ray film. Then quickly, they'll have to move on to the second phase, to analyze the data, as every 3 hours GLAST is going to film the entire sky. Egret would look at a piece of the sky for a week or two and took months to see the entire sky. The CNBG is ready. The Bordeaux researchers have been at work for months and years with simulations, and the software is ready to receive and analyze thousands of gamma-ray sources. Later, by comparing their gamma sky maps with pictures from other instruments and at different energies and wavelengths, they will learn more about the most violent phenomena in the universe.